everyone. Today we will have lecture 21. We have been discussing several corrosion events on the basis of mixed potential theory. In parallel, we have been solving numerical problems and trying to assess the effect of several factors like a number of oxidizing agents present in an electrolyte on the corrosion of active metal, effect of exchange current densities, effect of galvanic couple, and at the same time effect of increase in area of either cathode or anode, and then see the change in the corrosion rate of the active component. We have also discussed cathodic protection, and we could see that there are two modes of cathodic protection. One is ICCP, that means impressed current cathodic protection, as well as another one is sacrificial anode. And we could see the analysis of cathodic protection on the basis of mixed potential theory. We could also see the effect of velocity, and in all those situations we could see that the effect is in the active zone of the metal which is dissolving, and that interaction point between the polarization graph of cathodic polarization as well as anodic polarization, but all the time we have considered the anodic polarization to be activation controlled. And then we started solving some problem when we on the particular situation, that if the potentials are not measured with reference to hydrogen electrode, rather than if we measure the potential of the polarizing electrode on the with respect to some other standard electrodes like Ag silver chloride, copper sulfate, or saturated calomel electrode, then what could be how we could solve a problem to find out the potential as well as the corrosion rate. And in fact, in the last lecture, the later part, we tried to understand some of the scale factors when we use saturated calomel electrode. And one problem we also solved, that if a platinum is polarized to some certain voltage, and that polarization with reference to oxygen evolution reaction, that means it is an anodic polarization, and the potentials were measured with reference to saturated calomel electrode, and we wanted to and the part that so we wanted to find out the amount of over voltage. So we put two scales, standard hydrogen electrode scale as well as standard saturated calomel electrode scale, and we could see that how to change those scales to find out the potential as well as over voltage. Now, before we move to another important aspect which can be analyzed with respect to mixed potential theory, that is the passivity, we need to solve one more problem just to make it clear that how to make use of electrodes, reference electrodes other than standard hydrogen electrode. So, first lecture 21, in lecture 21, the first part, the part 1, a problem will be solved, and that problem statement is like iron is dissolving in an acid at a rate of, let us say, 50 mdd, and the pH of the solution is 3, and we need to find out. So, the to find E core and I core, and the E core should be with reference to standard calomel electrode, and the other data which are provided, these are the two things we need to find out. Other data, this is hydrogen evolution is basically the reduction process. This is one. Second part is pH, of course, is 3. Beta, which is the Tafel slope, is 0.1 per decade of volt per decade of current density, and the process is activation controlled. Activation control. So, this problem we will try to solve, and we have to also see the another data, which is iron. Atomic weight of iron is 55.85 gram, and we are taking N to be 2. That means it indicates that this reaction is we are considering. That means 2 electrons are participating for the anodic process. So, this is the part 1, and part 2 will start passivation. Passivation, understanding and mixed potential theory associated with passivity. So, these are the two parts we will try to do today. In fact, once we solve this first problem, and the second half of the topic, we will just introduce passivity, and then in subsequent lectures we will keep continuing our discussion on passivation. So, let us try to solve the problem. Now, since it is mentioned activation control, that means we can draw mixed potential theory. This is log I potential. Now, let me draw everything with reference to standard hydrogen electrode, and since hydrogen ion reduction is the cathodic reaction, so we can have mixed potential theory like this. And one more data that is missing is I0 hydrogen over iron surface equal to 10 to the power minus 7 ampere per centimeter square. So, if we see this, so that means this point is I0 hydrogen over iron surface equal to 10 to the power minus 7 ampere per centimeter square, and this potential is E equilibrium hydrogen, and this particular quantity can be found out because we have mentioned pH to be 3, and this is at temperature T equal to 298 Kelvin, that means room temperature, and pressure hydrogen equal to 1 atmosphere. If it is not 1 atmosphere, then the calculation becomes little tricky, because that time we have to consider a reduction the Nernst equation with the partial pressure of hydrogen also. But if this is maintained at 1 atmosphere pressure, so my equilibrium hydrogen, this becomes 0.059 pH equal to 0.059 into 3 equal to minus 0.177 volt. Fine. So, this is the voltage that this particular point is minus 0.177 volt. Now, since beta is considered 0.1 volt, and if this point coordinate, if I try to find out E core, I core, so I core can be found out from this data, because we have already measured this. This is the value that is given 50 mdd, which is nothing but 50 milligram per decimeter per day. So, I can convert this one into gram, and decimeter can be converted into centimeter square. So, I can make it 10 to the power 1 square centimeter square, and day I can convert to second, 24 hour into 60 minute into 60 second, so second. So, this becomes my gram centimeter square per second. So, mdd can be expressed with this W by AT equal to I core iron divided by N F. Now, this side is 50 into 10 to the power minus 3 divided by 10 square into 24 into 60 into 60 equal to I core, that time would be I core ampere centimeter square. A is 55.85 divided by N is 2 and F is 96500 coulomb. Okay. So, I could see that this unit, both sides the units are same, because ampere is nothing but coulomb per second. So, then it will match this unit it will match. So, I can find out I core equal to 50 into 10 to the power minus 3 into 2 into 96500 divided by 10 square into 60 into 60 into 55.85 ampere per centimeter square. So, this would become, if you calculate, it will become 1.0 into 10 to the power minus 5 ampere per centimeter square. So, I core equal to 0.0 into 10 to the power minus 5 centimeter ampere centimeter square. So, that means at this point we know this value. So, now we have to find out this quantity. So, in order to find out, we have to use cathodic over voltage, which is minus 0.1 log of I core by I0 hydrogen over iron surface, since at this point IC equal to IA equal to I core, and this point is also known. So, I can find out over voltage of this amount, and then I get the, so I get E core minus E equilibrium hydrogen equal to 0.1 into log 10 to the power minus 5 minus 7. So, E core equal to minus 0.177 minus 0.2. So, this E core becomes minus 0.377 volt. Remember, because when we calculate this E equilibrium hydrogen, that is based on pH, and this equation is with reference to hydrogen electrode. So, that is what initially we have taken everything on the potential axis in hydrogen standard with reference to standard hydrogen electrode. So, whose potential at room temperature is 0. So, now once we find out this value, that means this is with reference to standard hydrogen electrode. So, now in order to find out E core with reference to saturated calomel electrode, so we have to find out two scales. So, these are two scales. This is standard hydrogen electrode, where this point is 0 volt, and this is standard calomel electrode. So, the 0 point corresponds to minus 0 plus 241 volt. This is the standard calomel electrode. E is equilibrium equal to 0.241 volt. So, this is the standard voltage of standard calomel electrode with reference to hydrogen electrode. So, that will be considered as 0 when we measure any voltage with reference to standard calomel electrode. Now, so this potential is with reference to standard hydrogen electrode. So, the standard hydrogen electrode, this is minus 0.377 volt. So, corresponding data, this is the potential we have to measure. So, that means we see that with reference to standard saturated calomel electrode, the potential will be this difference, and since this is 0, so this potential also will be negative, and this potential would be 0.377 plus 0.241 with a minus sign. So, this becomes 811 volt. So, this would be equal to minus 0.618 volt. So, this is the problem I wanted to show, how to make use of different electrodes or reference electrodes. Now, in case of different reference electrodes, this value, this equilibrium value will be different. In case of saturated calomel electrode, this is the voltage. In case of silver chloride electrode, or in case of copper sulfur electrode, the equilibrium potential of that reference electrode will be different, and that particular equilibrium potential is measured with reference to standard hydrogen electrode, and that becomes 0 because we are taking that particular potential to be a reference potential. and accordingly you have to make use of and change the values as per this scale, this particular scale. Side by side you put those two scales and find out what could be the potential that will be shown in the machine. Okay, so this is the problem I wanted to solve. Now this is actually taken from a book. Similar type of problems are there in another book, which is an introduction to metallic corrosion and its prevention by Raj Narayan. In that book some problems are there. In case of the problem what we solved last class, that was available in the book Principles of Corrosion Engineering and Corrosion Control by Zaki Ahmed. Okay, so you can read those two books where you can find a lot of problems. In fact, in this course also you will be given a lot of numerical problems in after subsequent weeks. So you need to solve those problems, and the TAs will be there, and I will be also available for discussion. So this actually we now gradually move to the second part, which is the passivation. So the second part is passivation. So and this passivation is extremely important engineering field. For example, this is very popular that stainless steel. You use stainless steel in many applications, many critical fields like chemical industries, like acid making industries, and even our day-to-day applications, the stainless steel utensils, as well as stainless steel bioimplants, even stainless steel tools, and everywhere we have this word called stainless. Stainless means it does not get corroded, and we all from a normal textbook we have found out that we know that stainless properties from the stainless steel comes due to the effect of chromium. Since stainless steel contains let us say 304, which is a very popular grade of stainless steel, it contains nickel and chromium. Chromium is of the order of 18 weight%, nickel is of the order of 8 weight%, and of course carbon is very low. It ranges from 0.02 to 0.03, and sometimes it contains little higher carbon content, which is 0.08% it might go. So the carbon is generally in the lower range, and the intention is always to go for a very low carbon, just to avoid sensitization, because sensitization is a tricky problem as well as it is a very critical problem in case of stainless steel, where grain boundaries are attacked preferentially by the chemicals. So there this chromium tries to form chromium oxide on the surface, and once this chromium oxide forms on the iron surface, it becomes a near inert. That means in the environment where it is used, where once chromium oxide forms, it does not participate in dissolution reaction. So that means the rate of dissolution decreases to a great extent. The reduction in rate can reduce from, let us say, some orders of magnitude. Let us say in normal condition, iron, if you expose it to some acid, it can dissolve at a rate of 10⁻⁻5 ampere per centimeter square, which is extremely high corrosion rate. But once we add chromium, the corrosion rate can reduce to up to 10⁻⁸ ampere per centimeter square. So that means the corrosion rate reduction is almost about 3 orders of magnitude. So that is the influence of chromium there, and this particular behavior appears because of the very tendency of that metal with chromium content to passivate in that environment. So this passivation is nothing but the reduction in corrosion rate due to the influence of environment or influence of alloying elements in the metal. Okay. So for example, if lead is exposed to sulfuric acid, it can form lead sulfate, and that lead sulfate can give reduction in corrosion, and that is also getting passivated. Okay. So, that is basically the environment is leading to sulfate formation. But in case of iron, if you expose it to water and then if you anodize it, that means if we take it preferentially, take it intentionally to the anodic side, let us say potential, equilibrium potential is minus 0.5 volt in case of iron, if you put it in water, and if you take it to a positive potential, let us say close to around 1 volt, it might passivate again because of the formation of different degrees of iron oxides or hydroxide. Okay. So, and that will be decided by the pore bed diagram of that iron. So, that means the passivation, as we discussed, that passivation is nothing but the reduction in corrosion rate due to the influence of environment or the influence of the alloying elements in the metal, or it has a self tendency due to anodic polarization. Okay. So, now on this passivation, people have extensively worked, but the first time it was realized by the great Michael Faraday. In 1836, he did one interesting and a very simple experiments. Those experiments can still be performed in normal condition. In your house, you can have this particular experiments. Of course, you have to take care of your safety, because you have to deal with nitric acid, concentrated nitric acid, that is 70% nitric acid. So, you have to be very cautious, and always you have to put on gloves and all the safety procedures before you do this experiment. But this experiment is basically the start of passivation discussion. So, in 1836, around that, Faraday did one experiment, iron with HNO3. This was a famous experiment. The experiment starts with the container containing HNO3, 70% rich NO3. HNO3 is very concentrated acid at room temperature, and of course, atmospheric pressure. Fine. So, this is the condition, and there if we introduced one iron block, a freshly prepared polished iron block, if we introduce into it, what it does, initially you will see that there are bubble formation. Initially, of course, there will be small bubble forming, but after maybe couple of minutes, you would see that the bubble formation has receded, and no more bubble formation is there. Now, if one starts taking weight of this iron object, one can see that the iron object weight reduction is not possible to measure with a normal weighing machine. If you have a very sensitive digital weighing machine, you can check the weight loss, you can get the weight loss, but otherwise it is almost negligible weight loss, because the corrosion is nothing but the weight loss. But here you do not see any weight loss. Now, if we continue that experiment in this fashion, so if we have HNO3 70% and that metal is still there, now keep adding water. So, when you add water, you are actually diluting it. When you dilute it, that time you would see that there is no visible effect. that means, and at the same time if you keep measuring the weight of iron with time, it does not change. So, there is again negligible weight loss. Now, once we take this iron again, now with so the second time, this is the second experiment, this is the third, this is first, this is second, and the third one. So, the dilute, this is dilution. Now, this is still dilute and still that metal iron is there without any change. And now take a glass rod, a sharp glass object, and then scratch this iron surface. This iron surface, if you scratch, you will see that vigorous bubbles are forming on the surface and gases are coming out. If you analyze this gas, you will see this gas is nothing but NO, and we see weight loss and this weight loss is substantial. Now, this particular metal, this from this condition stage 2, if you take it and then put it in the dilute acid HNO3 with a scratch on it, then also you will see that gases are coming out and the bubbles are forming, and the gas is analyzed, you will see that this gas is NO, and you will see lot of weight loss. So, this is the experiment what Faraday performed. Now, this experiment talks about passivity, as well as later on it talks about when it converts passive to the active stage. So, the type stage 1, the metal is actually the iron is passivating and then reaches to passive condition, and corrosion rate reduces to a very large extent. Now, stage 2, since that metal has attained passivity, that means on the surface something has happened, and if you do not disturb it, and this water when you add it should be added slowly, so that it does not create much of churning in the metal, in that water, in that solution. So, that condition is still passive, but once you create a scratch, that scratch actually removes the surface layer, and that surface layer is actually introducing passivity into that particular metal, and once it is exposed, the passivity is broken. So, this particular stage is a broken passivity, and this particular stage it goes to active from passive. So, this is the phenomena we will observe. Okay. So, that means passivating, still passive, and here also the same situation is taking place. So, this is active. So, we have passive, and another interesting part is if that fresh iron metal, when it was first introduced into the concentrated HNO3, if it is introduced instead of concentrated HNO3, if you introduce the dilute HNO3, you will see that the bubbles are forming. So, it is not passivating, and you will see that there is a huge water loss, the weight loss will be consistent and there will be substantial weight loss. So, that condition of course is an active stage. So, we are getting active to passive, passive is maintaining, and at the same time because of the surface disturbance it becoming active again from passive state. So, this is the very experiment of the great Michael Faraday, and this talks about the passivity from active to passive as well as from passive to active, and it gives a lot of informations, and that is the beginning of extensive research on passivity as well as passivation, because this particular aspect has got a huge industrial as well as practical implications. So, let me stop here. We will continue our discussion on passivation in our subsequent lectures. Thank you.